Hello everyone. So in this class we've done a lot of different things. We looked at some concepts of turbulence. We looked at different scales. We learned about the energy cascade. We looked at strategies related to direct numerical simulation, where the scales are going to be resolved, until what scales are they resolved. Then we've moved on to large eddy simulation. So a lot of different classes have been spent on learning quite a few concepts in turbulence, right? Now, what we are going to do in the rest of the classes is to try and actually work out problems so that we can apply what we have learned to real things. Okay, we'll start slow. We'll start with some simple problems. In fact, the first couple of problems will be related to vectors and probability density functions. Then we start to move on to Fourier transforms and derivations in the Navier-Stokes equations and so on. So let's get started. So this is the module 11 where we discuss, where we try to work out as many problems as we can. So we have about 12 problems in this module and we'll try to work them out. Most of these problems are from Pope's book. Let's start with the first problem, and this is a relatively simple problem here. You have the momentum equation given for the compressible Navier-Stokes equations for a monoatomic gas, and it's given by rho del u del t plus u dot del u equals minus del p minus del cross mu del cross u plus 4/3 del mu del dot u plus rho f. Okay, this could be just a body force, but as you can see, the equation is written in vector form. Remember, u is the bulk velocity of the fluid, p is the pressure, rho is the density, mu is the dynamic viscosity, f is the acceleration due to the external body forces acting on the gas. We have to rewrite this equation using tensor notation. That's what we have to do. We have to rewrite this equation using tensor notation. So how do we do it? Right? I'll give you a few seconds, almost a minute, to try and think about how you can do this. How do we work it out? Remember, everything is given in vector notation. In the cross product, we will have to convert it into the appropriate notation for index notation. Same thing for dot product. Derivatives, we will have to use it accordingly. It looks like dynamic viscosity is not a constant. It's a function of probably space. So you can leave it as such within the derivative, within the del cross. You understand what I'm talking about? Right here. The del p, which is a gradient operator. This is a gradient operator. This will also need to be written in index notation, of course. How do we do this, right? Okay, let's check it out. I'm going to rewrite the equation. So rho del u del t, and u is a vector, of course, plus u dot del u, isn't it? U is a vector, equals minus del p. P is a scalar, but del p becomes a vector, minus del cross mu del cross u, isn't it? Plus 4/3 del, and then you will have mu del dot u, u is a vector again, plus rho f. F is a vector. Okay, how do we do it? So let's use the index I to represent the fact that this entire equation is for the I direction. Okay, so then I will have rho del ui del t. Okay, del ui del t, and then here what I'll have is I'll have ui, but here I can use uj del j, isn't it? Uj del j ui. So now it is in index notation of I. Okay, so now the left hand side is done, and I now have the gradient operator, which again I want everything in the direction I, so this will be minus del IP. Okay, remember everything is in the direction of I as I am noting it here. Then I'll come to this term in a bit, this del cross term, because that is actually going to be the more complicated term. I'll start from the body force. It's a relatively simple term to do. So that would be rho Fi, because it is in the direction of I. Now here again, I want it to be into the direction of I, so the last but one term, so that would be 4/3. And del dot U, I can write it as, I can use a dummy index here, so del J Uj and mu. Then of course I will have del I here. So now everything is in the direction of I. And the dummy index, I have used it as del J Uj. Okay, so here what happens is, now I will have minus, and instead of the del cross, what I'll need to use is the alternating tensor. So I'll have the epsilon, and since it has to be in the direction of I, the starting index would be I. Okay, now what I'll do is, I'll do the inside first. I'll do the inside first, and what I'll have is, I'll use say two new indices. So I'll bring in, because there is a del cross, I will need to bring in an alternating tensor there again. Okay, so then I will have, what I'll do is, I'll have epsilon, and then I will have del M U J. Okay, so then this is going to be LMJ. Okay, epsilon LMJ, and since my last one is I, this is going to be del M, correct? Del M, and I can have this as IML. Okay, so I'll have this as IML. Let me see. I'm sorry, I used multiple M. So this would be, of course, there would be an epsilon I. That much I know. But this is LMJ, MJ. Fine. So this one, the direction is L, isn't it? So then I will have L in the end. And then I can bring in a new one, K, so then I will have del K. Del K, and this whole thing in the square bracket is L, so then I will have epsilon IKL. So now finally everything is in terms of I. So I have rho del T of Ui plus Uj del J Ui, so now everything is in terms of Ui. And then here also minus del IP, again in direction of I. Okay, coming back to the last term, it is rho Fi, so in the direction of I. Here too, it is in the direction of I, because this is just a dummy index. And then finally coming back to this complicated cross product term, I'll do the inside first, so I'll have mu epsilon LMJ. Epsilon is this alternating tensor right there, right? So it's a permutation tensor. So epsilon LMJ and del M Uj. So then epsilon, it will be as epsilon LMJ, and this stuff in the square bracket will be in the direction of L. And because I have a del cross on the outside, I will have a del K. And then finally everything in the direction of L. So my last alternating tensor is going to be IKL. I hope that is clear. So this is your equation in index notation. This is your final answer. So I hope this makes sense. Okay, let's try another problem. Okay, so here this is the second problem. By expressing the instantaneous pressure, density and temperature as P is equal to capital P plus P prime, rho is equal to rho bar plus rho prime, and T is equal to T bar plus T prime, where capital P, rho bar and T bar are the mean or time average components, and P prime, rho prime and T prime are the fluctuating components of pressure, density and temperature respectively. Perform a Reynolds time averaging of the ideal gas equation P is equal to rho RT and determine the Reynolds average pressure for ideal gases. Okay, so in class we had done the Reynolds averaging for the Navier-Stokes equations. This is obviously relatively simpler, we just have to do it for the ideal gas equation, but you need to understand the concept of Reynolds averaging. So how do we do this? Right? How do we do a Reynolds averaging for the ideal gas equation? All you need to do is decompose each and every term in the ideal gas equation into its mean and fluctuation, and then you average both sides. That is what you need to do. So let's try to work it out. So I have P is equal to rho RT, and my P is capital P plus P prime, rho is rho bar plus rho prime, T is T bar plus T prime. So I'll substitute all that in there and I will have capital P plus P prime is equal to, I will have rho bar plus rho prime times R is a constant, right? It's a gas constant. Temperature, of course, I need to split it, decompose it. So T bar plus T prime. This is what I have. So on the left hand side, I will have P plus P prime, capital P plus P prime. And on the right hand side, I just multiply it out, isn't it? I just multiply it out. So I will have rho bar T bar, then rho bar T prime, then rho prime T bar, and rho prime T prime. This whole thing multiplied by R. Now what I do is I time average both sides. I time average both sides, and then what I have is I will have P plus P prime average is equal to rho bar T bar plus rho bar T prime plus rho prime T bar plus rho prime T prime, the whole thing times R, of course, and average of the whole thing, isn't it? Now here I have average of the sum of two components. I can just take average of each one. So then what I'll have is P bar plus P prime bar equals. Now if I'm going to split each term. So I'll have rho bar, T bar, and the average of that. So that just becomes rho bar T bar, because you cannot take a time average twice. Even if you take a time average twice, you get the same thing. So rho bar T bar just becomes rho bar T bar average just becomes rho bar T bar. And then I'll have rho bar, now that comes out because that is already an average, T prime bar plus rho prime bar T bar, isn't it? Because the average of T bar, and when you take an average of it again, you still get T bar again. But the rho prime, there when you're taking an average, you get rho prime bar plus rho prime T prime. Now that's a correlation. You will have to take an average of both of those, and that you cannot split. This whole thing multiplied by R, of course. All right. Now, based on what we know, the average of the fluctuation, right? The time average of the fluctuation comes out to be 0. Any term, you're taking a time average of the fluctuation, that will go to be 0. So this term will go to 0. This term will go to 0, and this term will go to 0. So on the left hand side, you're only left with P bar, isn't it? Actually, based on our notation, it should just be P, isn't it? It should just be P. So just a notation difference, we're just calling it P. So on the left hand side, you just have P. And On the right hand side, what I have is just two terms. So rho bar r t bar plus rho prime t prime bar and r. Isn't it? This is what you have. So this is it. So your average pressure is rho bar t bar r plus rho prime t prime bar times r. Okay, so the product of the two means plus the mean of the product of the two fluctuations. The whole thing multiplied by r, of course. This is your final answer. I hope this is clear. So all we did was we took the ideal gas equation, we split it up, we decomposed it into average and fluctuation, and then we time averaged both sides. That's what we did. All right. Okay, let's go to the next problem. This has to do with PDFs, probability density functions. Problem number 3. For the following uniform distribution, f of v is equal to 1 over b minus a for a less than or equal to v less than b, and 0 for v less than a and v greater than or equal to b. What is v? V is the sample space variable, remember? F of v is what? It is the PDF, probability density function. You have to show that the variance of u is 1/12 b minus a the whole squared. The variance of u is 1/12 b minus a the whole squared. How do you do this? So in order to calculate the variance, you will first require the mean. Okay, so let's see. I have my f of v as 1 over b minus a when v is less than b and greater than or equal to a, and it is equal to 0 otherwise, right? Now, in order to calculate the mean is given by, this is how we represented the mean. It would be integral 0 to infinity v f of v dv. This is how you calculate your mean. And your variance of u, isn't it, is v minus u bar, sorry, not u bar, mean of u squared f of v dv, 0 to infinity. These are your definitions. Here is what you can do. Now, in order to calculate variance, you will need mean. So let's calculate the mean first. The u mean is integral 0 to infinity need not be taken because the function is only defined from 0 to a to b. It is 0 otherwise. So your integral can just be from a to b. So you will have a to b v times f of v dv. So that would be equal to a to b. And what would you have? You would have v over b minus a dv going from a to b. So that would be v squared over 2, isn't it? 1 over b minus a times v squared over 2 going from a to b. So that would be b squared minus a squared over 2, or b squared minus a squared over 2 divided by 2 times b minus a. So that would be a plus b divided by 2, isn't it? That is your mean. Your mean is a plus b divided by 2. A plus b divided by 2, just so that we are clear. This is, let me just write this clearly. Yep. The mean is a plus b divided by 2. So you have gotten the mean. Okay, you see how this happened, right? Because I have a b squared minus a squared over 2 times b minus a. So that is b minus a times b plus a divided by 2 times b minus a. So that's how both of those could cancel, and you just have b plus a divided by 2 or a plus b divided by 2. So that is your mean velocity. Now, in order to find out the variance, here is what we do. Okay, so your variance of u is going to be equal to, again, a to b, and you will have v minus u mean, isn't it? So v minus, what is the u mean? It is a plus b, a plus b over 2. So that would be a plus b over 2. So that would be a plus b over 2, correct? Like this. And this thing squared, then f of v. So 1 over b minus a dv. Is that clear? So I have v minus a plus b over 2, the whole squared, times 1 over b minus a dv. Now I have to integrate this. Just so that I can make my integration slightly easier, what I'll do is, I will make the substitution that s is equal to v minus a plus b over 2 divided by b minus a. I will make this as my substitution. That s is equal to v minus a plus b over 2 divided by b minus a. So that means 1 over b minus a dv is equal to ds. Okay, so I already have that in my integral. Then as far as the limits are concerned, when v is equal to a, what does s become? When v is equal to a, what does s become? S becomes minus half, isn't it? You just have to substitute v is equal to a in here, and you will have a minus a over 2 minus b over 2 divided by b minus a. So that would be minus half, because a minus a over 2 becomes a minus a over 2 becomes a over 2, and then you have a minus b over 2 divided by b minus a, so s becomes minus half. When v is equal to b, s is equal to plus half. So your variance of u becomes the integral of minus half to plus half, isn't it? And it would be s squared ds. S squared ds, but keep in mind, because it has to be s squared, the whole thing will have to be multiplied by b minus a squared. It would have to be multiplied by b minus a squared just so that you can get this part in the denominator. Just so that you can get that part in the denominator. So because of that, you have to multiply by b minus a squared. So the integral of this is s cube over 3, and of course I have a b minus a squared, and s cube over 3 goes from minus half to plus half, isn't it? S cube over 3 goes from minus half to plus half. So I have b minus a the whole squared multiplied by s cube over 3 going from minus half to plus half. Now if I do this, I will have b minus a squared multiplied by, I would have half. When I substitute it there, I'll get 1 over 24, isn't it? S cube over 3, 1 over 2 cube divided by 3, 1 over 24, and then I'll have plus 1 over 24, not 12, 1 over 24. So that would be b minus a squared divided by 12. That is my variance of u. Isn't that what I had to prove? That 1 over 12 b minus a the whole squared. And that's what I got. 1 over 12 b minus a the whole squared. Here it was just simple integration. All I had to do was just make a substitution such that my limits become more straightforward to calculate. And what I would have is, if I just make the substitution that s is equal to v minus a plus b over 2 over b minus a, and then I don't have that divided by b minus a squared, so that is why I end up multiplying by b minus a the whole squared, and then I have s squared ds, isn't it? I have s squared ds. I end up multiplying by b minus a the whole squared just so that I can get my s squared completely. Now this 1 over b minus a times dv basically gets lumped into this ds, isn't it? 1 over b minus a times dv becomes ds. So all that just plays out very well, and then I have the integral of minus half to half s squared ds. Of course, this whole thing multiplied by b minus a the whole squared. S squared ds becomes s cube over 3. Limits are now minus half to half, and then when I do that calculation, I get b minus a the whole squared over 12. So I hope that was clear. So this was a problem in PDFs where we had to derive what the variance was, and we just did. I hope that was clear. That's it for today, and then now we will move on to more problems in the next class. Thank you.